Physics students, we're going to finish up the notes here. So let's start off, let's talk about powers of 10. So when we're working with large numbers larger than 1, different multiples have different names, and so we'll go with some of the common ones here. So multiple, like if you have a decameter, that's 10 meters. If you have a kilometer, that's 1,000 meters. Mega means 1,000,000, and then giga means 1,000,000,000. Okay, and just correspond those. 10 to the 9 is 1,000,000,000. 10 to the 6 is 1,000,000. 10 to the 3 is 1,000. All right, so on the smaller than 1 side of things, so deci is 1/10, so a decimeter would be like 1/10 of a meter, or 10 to the minus 1. Centi is 1/100th, or 10 to the minus 2. Milli is 1/1000th, 0.001. Then we'll jump a few. Micro is 1/1,000,000th of the unit. So there would be 1,000,000 micrometers in a meter, or another way you could think of that is that there's 1/1,000,000th of a meter is equal to a micrometer, and then also nanometers. All right. So when you're working with powers of 10 on a calculator, the easiest way to do this numerical entry is usually to locate the E or EE key, and that stands for exponential, or really it's just another way to express scientific notation. So that EE button on your calculator, and most phones operate with that. They have one of these as well. It'll be a capital E or 2 capital E's by each other, and watch out for the lowercase e, because that's usually something different. So on your calculator, if you're trying to enter 6.5 times 10 to the 9th, then you're going to press 6.5, that EE button for exponential. It'll give you 6.5 E9. And a computer entry, it would look like these over here. And make sure that you're using the negative key here as you're entering the negative exponent. And I have TI Inspire emulator here, so I'll pop that up real quick, and I'll show you what that looks like on an Inspire, because I think some of you may have your own of that calculator. All right, so let's make this a little bigger. All right, so let's do this in a calculator. So 6.5, and then all I have to do is hit the E button, which is right here. See the EE, and then 9. And because of whatever mode I have the calculator in currently, it's doing like float or whatever, so it writes it out this way. But it also might appear, depending on what mode your calculator's in, as 6.5E9, and that is a real number. Okay, and we could repeat the same thing with the other number, but I'm not going to spend your time doing that right now. Okay, so you can go on and explore with the interactive calculator here on page 45 in your book, so please make sure that you go and do that on the online version of the book. And take these numbers and put them in scientific notation. So 4,184, we would do this so that the first digit is between 1 and 9. So 41 would not be between 1 and 9, but 4.1 would. So we're going to take the decimal place as it currently is, and it would move over 3 places to be 4.1 4.18 times 10 to the 3. Remember, it's going to be a positive exponent because that number is greater than 1. All right, 0.035 meters, that number is smaller than 1. Move the decimal place 2 places over to make it 3.5. Remember that first digit, you want a number there between, well, maybe I should say we're going to move the decimal place so that there's a single digit to the left of the decimal place. That's another way to think about it. So 3.5 in the end, we move the decimal 2 places, so 3.5 times 10 to the minus 2. Or the exponential notations over here. You see those as well. All right, so far we've talked about fundamental quantities. There are only 7 fundamental quantities that we talked about at the beginning, and there are dozens of derived quantities, if not more than that. Maybe dozens of common ones that you could encounter in physics. So the fundamental quantities we've talked about so far are mass, length, and time. Speed is a derived quantity. Think about what you probably, like in your car, I'm going 35 miles per hour, or maybe kilometers per hour. So there are 2 units in there. And for speed, it's length and time. And those 2 quantities are divided by one another. So like 8 meters per second is a speed you might travel on a bicycle. All right, another derived quantity is density, and that is mass per volume. Now they say length cubed here, and volume, the units of volume are derived from length cubed. Surface area is another derived unit, so that is length times width, so that is like meters squared. All right, and then if you add volume, you just add the third dimension there, and that gives you, oh wait, no, we're still talking surface area. Okay, so the surface area of the entire cube now would be 54 square meters, because we'd have 6 sides with 9 by 9, so, or excuse me, 3 by 3, so 6 times 9 gives you 54. All right, and then it doesn't really matter where or what you're measuring the surface area of. The units are all going to be in meters squared. All right, here's a look at some common formulas for, formulas for surface area and volume for some common shapes. So there's the rectangular prism, the sphere, the cylinder, and for the cone. And so you can see the different ways that you would calculate the volume for these objects as well as the surface area. All right, density is another derived quantity, and I like the way they present this: the concentration of mass in an object's volume. So here's some comparisons there. Steel, the density is about 7,800 kilograms per meter cubed, whereas the density of air is about 1 kilogram per meter cubed. Now, just for kicks, when you convert this to like grams per centimeter cubed, for example, or grams per milliliter, steel would be 7.8 grams per centimeter cubed, and air would be 0.001 grams per centimeter cubed. Or you could do, or it would be about 1 gram per liter. So anyways, that's some thoughts there. And the symbol is a Greek letter rho. Sometimes you see it with a D instead of a rho as well, depending on the source. All right, so we're working, at least for now, with density in kilograms per meter cubed, mass in kilograms, and volume in meters cubed. But any unit of mass and any unit of volume here could be used to make a density. You just divide the mass by the volume and keep whatever units are used. All right, so go and explore with the density calculator on page 43. And you should be able to see that take this package, simply divide the two quantities to get the density. All right. And another thing you should be able to do with the equation is to play around and see that as you increase the mass, keeping the volume constant, the density increases. As you increase the volume, keeping the mass constant, the density decreases. All right, so pause, give yourself time to work these out, and then the answers are here. All right, again, which of these are recorded using SI units? Pause, give yourself time to work them out, and then here are the answers. All right, thank you for watching.